My name is Mason Peck. I teach engineering at Cornell University. I've been there for about 7 years. This topic, spacecraft on a chip, is one that's had some press lately. We had some prototypes flying on STS-134, which is the space shuttle mission before this last one, Atlantis, which just landed this morning. So, we were on TV and radio and so forth, and that was kind of a lot of fun because people are really interested in space. It really motivates people. I don't have to tell you folks this. You're spending your evening doing this as opposed to the many other things you could be doing with your time. So I don't have to sell this idea to you, but also for Ben and maybe my daughter, or people who are of that age when they're worried about what job they might get in the future. Maybe some of us are also in that boat. This is a pretty employable discipline, partly because there's always new stuff to be done. It's also pretty young, right? So there's a lot of new stuff that we could be doing. A spacecraft on a chip, the idea there is, just to cut to the chase, we're building satellites about the size of a thumbnail, for reasons I'll try to make clear. Something that size has neat physics, which I'll talk about, but also it makes space even more accessible to you and me. As a university professor, I don't make a ton of money. I'm not going to be able to afford to spend the $20 million to go to space adventures and get my ride up into space on Soyuz or something like this. That's not going to happen. But maybe launching a small satellite, that's within reach. So this is even smaller than those small satellites that are up there. At Cornell, this is just our standard kind of collage of crazy stuff we do. To try to convince you that I'm not completely blowing smoke, we've built a number of spacecraft in my lab. This is called CUSat. It's 2 spacecraft that are about the size of one of these chairs. They separate from each other and fly around each other and do some in-orbit inspection, it's called. That's neat. I could talk all day about that one, but I'm not going to. We also built this one. This is finished fabrication, and we're going into testing the software and doing mission operations rehearsals. It's called Violet. It's a spacecraft that has an ultraviolet imager, but its main purpose, its main reason for living, is to demonstrate very high agility spacecraft motions. There's very fast attitude motions. It may not be as fast as some of the rockets I saw, but in terms of attitude, this thing can rotate about 40 degrees per second in rate, so it's about that fast. Which might not strike you as very fast, but in fact, for a spacecraft, that's really, really fast. Hubble, you probably know, right? You're a Hubble mission operation. What's the slew rate, maximum slew rate on Hubble? It's like a fraction of a degree per second, maybe, right? 10th or 100th. Yeah, so a fraction of a degree per second. So it's the point of the Violet's program is, in fact, to demonstrate that very small things can move very fast. I don't move so fast, but little things move fast. And the smaller they are, the faster they go. It's just sort of a fundamental law of nature. So that brings us to our satellite on a chip project. Here's a dime. This is a prototype chip, and in fact, I've got it right here, and I'll pass it around. This is what we're going after. This is what we're going to try to make. So I know you guys are good at handling hardware, but this is not any kind of flight hardware. It's just sort of a demonstration, a test of how small we can make something. So you can pass it around. That's a 1 centimeter square chip with little gold regions that indicate what we might be able to put on the satellite. So our goal is to get to there in probably 2 or 3 years. We're getting close, and I'll tell you about that. We've done other things. We've sent satellites, we've sent students into space, or at least near space, on this Vomit Comet, the microgravity aircraft. They fly these parabolic trajectories, and for about 20 seconds, the students experience low gravity or microgravity. That's mostly just for fun. We do some experiments, but that's mostly for fun. We have a clean room, we have a thermal vacuum chamber, we have a couple of ground stations. One is on Kwajalein, that's where that picture is, which is in the Marshall Islands. It's where they launched the Falcon 1. And then these up here are CubeSats. So I want to spend a second and talk about what CubeSats are. Has anyone heard of these things before, CubeSats? Yeah, so they're satellites about the size of the palm of your hand or the size of a grapefruit. It's 10 centimeters on a side. And when those things were conceived in about 98 or so, 1998, the reaction in the community was, they're space junk, and even if not, what could you possibly do with something about that size? It's hopeless. They're hopelessly small, meaninglessly small. Each one of these panels, if you're lucky, maybe produces 2 watts of power. So it's very low power. Fast forward about 10 or 15 years, and every spacecraft prime contractor, we're talking about Lockheed, Boeing, Orbital Sciences, Northrop, they all have CubeSat programs, internally funded, some externally funded. Every government agency that sponsors spacecraft work sponsors CubeSats. They're a big hot topic, despite how small they are. So these small spacecraft, in fact, on the wall here, that's almost real size. That's about the size of these spacecraft. They can do a lot, it turns out. I'm an engineer, not a scientist, which means I'm interested in, I believe what the scientists tell me, and then I try to use that to somehow change nature, right? I want to build something new. I want to create something out of physics. These things represent what we call a technology push. That is, no one asked for a 10 centimeter cube satellite. NASA didn't say, give me one of these things. But the hobbyists, the university students of America came up with this idea, built this, and now people discover that they need it. So we're hoping that this model is roughly what's going to happen with our CHIP satellites. No one's asking for coin-sized satellites. And in fact, they bring up the same critiques. This is space junk. It's so small you couldn't possibly do anything with it. But I think we have some answers, and I'll talk about that in a second.
What's the orbital lifespan of something like that, or the chip?
That's actually a key question. So this obviously depends on the altitude, right? The lifetime, do you mean in terms of surviving or due to drag?
Because of the mass, because it's so much smaller.
Right, so it's a matter of ballistic coefficient, right? So the smaller something is in general, the worse its ballistic coefficient, or the lower it is. That is, the less it acts like a bullet. So drag is more pronounced on something this size than something of the same density, but just much larger. So drag tends to pull these back into orbit in, I guess, if you're anywhere below about 400 kilometers, it's easily within 10 years. It's probably within a couple of years, depending on the orbit. But it really does depend on the orbit. The chips, though, this is an important point. If we launched these to the International Space Station altitude, which is about 325 kilometers, they last about 3 days. So the space junk argument doesn't really hold here. They tend to clean themselves up out of Earth orbit. And that's a good thing. I don't want debris to bring down the space station, whether it's my fault or anybody else's. So this is a key benefit. But there's actually other reasons, science reasons, why you want that. Everyone get a chance to see the 1 centimeter chip? That's a very tiny satellite. It'll never compete with the Hubble Space Telescope. But what I'd like to do would be not to be too preoccupied with how things are currently done, and instead be a little bit more imaginative, or sort of feel free to be imaginative. The NASA Institute for Advanced Concepts was one of the last parts of NASA that funded engineering research before. So NASA's lost, I don't know how you count it, close to 10 years now without research in engineering. They are way behind where they might be. Whether or not you agree with the current administration's plans for a spaceflight, at least they have tried to grow this new Office of the Chief Technologist, which will bring research back into the NASA world. So they're actually sponsoring things like this. Now, NASA hasn't yet sponsored us. I've asked for some money, but we'll see what happens. But at least we have a shot with the way that NASA is currently configured. We'll see how long that lasts. So this picture, by the way, was from a Popular Science article they wrote about our project about 2.5 years ago. This is a picture of Jupiter and one of its moons. The idea here is that you might be able to send these little chips floating down through the atmosphere of one of the gas giant moons and get some data in a way that you couldn't otherwise. I'll say something more about that. All right, so how small are we talking about with these little satellites? Our objective is way down here in the tens of milligrams. It's really small. What I passed around here was probably about 50 milligrams, maybe even a little bit heavier actually. What we would do to this is to etch away most of the silicon, leaving just a thin foil, so it's really extremely lightweight. All right, so that's our objective. Just as a range to get you thinking about size, the International Space Station is something like 400,000 kilograms of mass. A geocommunications satellite, it's maybe 5,000, maybe even more kilograms. What they call a nanosatellite, which, by the way, sometimes includes CubeSats, sometimes not. A nanosat these days is something like maybe tens of kilograms, you know, the size of a heavy grocery bag. A CubeSat is about 1 kilogram. What we sent up on STS-134, the demo or the prototype of this chip, weighed about 1 gram. I'm sorry, about 10 grams. And I'll pass that around too. So that's this. 3 of these are currently stuck outside the International Space Station. So this is actually functioning. If you took this out in the sun, it would start beeping in RF. Go ahead and have a look at that. Don't try to pick the pieces off of it, but you probably can't hurt it if you just handle it normally. What you'll see on there are solar cells a combined integrated circuit that does digital signal processing and has a radio built in. So it's a computer and a radio built in a single integrated circuit. There's some power electronics and this little patch antenna. That, by our calculations and from our ridge testing on the ground, is enough to communicate from the International Space Station at 325 kilometers all the way to our ground station, at 0 on the ground. And also with a little bit of downrange. We think its range is about 500 kilometers if we use our $200 ham radio antenna. If we had that big APL antenna, for example, if we could use that one, the range would be close to where the moon is. So it's an interesting fact. Now, this is not just radio communications. It's actually kind of more subtle. Without going into tons of detail, we rip off some cell phone technology to make this work. We actually encode every bit with a special sequence that we can pull out of the noise in a way that I can explain if you want. But one thing I want to emphasize is that we are trying to use contemporary technology and contemporary parts to build this thing, even though they're not space-worthy. These are not space-qualified components. This TI chip that does all the processing and has a built-in radio, it costs about $2 a piece. It's not ready for space. But if I could build, one of these for about $3 or $4, I could maybe build 1,000 of them. And if I only need, let's say, 10 to survive, all I need is a 1 in 10 rate, or maybe even 1 in 100 reliability for this even to work. So I could get around the problem of not having high-tech, space-qualified stuff just by launching a whole lot of them. That'd be one way to go. But there's other reasons to do this as well, and that has to do with the physics. So the pictures are space station, Cassini, nanosatellite, the CubeSat we talked about before, and our prototype, and then our objective, which is tens of milligrams. So here it is in another view. You can see a little bit better. There's a quarter. What I'm passing around there, that's got a patch antenna on it, which is not the best. A better design would actually be 2 wires sticking out of it. It would be a so-called center-fed dipole antenna. This is a loop antenna built on a very thin sheet of plastic. And then this silicon substrate holds the solar cells, the radio, and other electronics that matter. This design, even more interesting, has a GPS receiver on it. Okay, so it's not just solar cells and a microprocessor and a radio, it's also a GPS receiver, which we need because there's no way you're ever going to track this thing, right? Probably from a few miles away, no radar will ever discover this thing. And in space, forget about it. So it has to tell us its own location. And the thing is that this GPS, I'm not really claiming this is a great discovery of mine or anything. These are off-the-shelf GPS receivers used for cell phones. And just super tiny. If you're willing to buy about 1 million of them. Now, I'm not. I want to buy one. But there are ways to get around that. So that's an interesting fact. So rather than being this sort of conservative, not to pick on NASA or Lockheed, traditional aerospace company and go for high reliability, building one exquisite spacecraft, I'm going exactly the other direction. I'm going for low reliability because I can build many of them and then get reliability back when I build a lot of them at the same time. And that way I can leverage all these contemporary off-the-shelf technologies, which of course are a lot cheaper. All right, so it's a different philosophy. Our timeline is this. We've launched this, and you're going to ask what we've heard. I'll tell you in a little while. We've launched this thing. This is the shrunken version we will probably launch next year sometime. But that's even a generation behind this, which is the objective system. That one will be a single integrated circuit. We'll work with a chip fabrication company to fabricate the entire system here on a single integrated circuit, we hope.
What will you launch with?
That's a good question, and it's one I want to ask you, to be honest. I'm looking for some clever ideas about how to treat this spacecraft differently from how we treat the large spacecraft that we launched today. Even those CubeSats have to launch on a spacecraft that'll get it to orbit, right? And it's kind of unavoidable that you have a huge launch vehicle to get at least past the atmosphere. But maybe there's something smarter you can do. We got lucky with this. There's a good story behind how we got this into space. We already know that we could launch about 1,000 of these inside a CubeSat. So if we build a CubeSat, put these inside the CubeSat, and the CubeSat goes on top of a launch vehicle, they have these things called P-pods, which are sort of shrouds that hold the CubeSats in and pop them out with a spring. So that would ride on top of another launch vehicle as a secondary payload. So this is sort of like a quaternary, is that the word? So this inside a CubeSat, inside the P-pod, and on a secondary launch. It's several layers deep inside the launch vehicle. That's how we have to do it now. That seems very wasteful to me. If you could do something dedicated, what would you do?
Put it on a small rocket that'll get to orbit.
I agree. So what, you have one in mind?
Mike. Yeah, not the cow.
So you want to go to orbit, or you just want to get to space?
Well, so there would be different applications if you just got it to space, and we could talk about those. And one would be, okay, you remember this Chinese anti-satellite experiment from a few years ago?
Right.
Okay, so there's a question about just how these debris clouds extend, just how they propagate, how they grow.
That they denied that existed.
Yeah, it's as hard as I work to keep debris out of space, in one act they actually added roughly 30% more debris with that one explosion. So it's disappointing. So the idea would be maybe you could launch a cartridge of these little chip satellites, and remember each one has its own GPS position on board, right? Furthermore, when these things send data to the ground, they send it in a unique way. It's the same way that cell phones don't confuse one another's signals, right? So we can individually receive each GPS signal. So we know the position and the identity of each of those positions. And as we track those through time, we get little streamlines, we get little path signatures that would tell us where this debris cloud or the simulated debris cloud would go. So in fact, you could try to replicate something like that Chinese ASAT disaster. You could try to do that in a scientific way and actually try to get measurements of what happened or what kind of thing might happen in the future. So that would be a neat application that would just involve getting it to sounding rocket altitude.
What is 100,000 feet by?
You could look at the mesosphere, right? Is that 100,000? A mesosphere is like 80 kilometers, right? So what is that in feet?
I think it's still in the stress.
Yeah. If you can get a little bit higher, there's this thing called the mesosphere or the ignorosphere. This is just below the ionosphere and kind of above the stratosphere, right? Where it's too low for satellites because they just burn up there, and it's too high for aircraft. So occasionally you can get maybe one or two measurements from a sounding rocket, but if you could distribute these high up in the atmosphere, they would flutter down to the ground because they're very, very low ballistic coefficient. And you might actually be able to map out scientific phenomena in the mesosphere, which we don't know how to do right now. So that would be a neat application. And I'm sure the Navy or the Army might be interested in that. So I think the thing is that there are a lot of applications for this because no one knows it exists yet, right? They haven't sort of gotten bored of this. We're getting a little bit bored of CubeSats now. We kind of know what they do. As interesting as they are, each one costs maybe $100,000 to get into orbit, which is kind of a lot of money still. It's maybe affordable for some organizations. University, you can write a good grant, maybe you can afford that. But these guys, we think it's a few bucks a piece. And that's actually inexpensive and is actually affordable. So maybe there's different kinds of science you could do where these are disposable as opposed to single spacecraft that have to work all the time. So let me just say a couple words about this experiment that we just launched. So here's Endeavour. Astronaut Andrew Feustel very kindly placed our experiment pallet on the outside of the space station, right around there, I think. This has been up there for a few weeks now, and we were very frustrated for a long time trying to look for the signals from this until we discovered that someone had vandalized our antenna and pulled out the coax cable. So you're like, man, it looks like we're just getting noise here. I don't know, it just looks like crap every time we get a pass. Well, that's why. So we're getting that fixed, and we'll let you know if we actually get some real data. So here's the 1, 2, 3 prototypes of the thing that we were passing around. They're on this so-called Jupiter pallet. That's on the Missy 8 experiment pallet, which goes on this overall structure here, which goes there on this big space station. Once again, it's very deeply nested inside another engineering system, which is kind of good because we're hidden from view. So we didn't have to go through a lot of NASA hassle to get this thing into space, which is amazing that we didn't. So it started off in the shuttle payload bay. The astronaut is retrieving this from the side of the payload bay. Again, this is a shot from Endeavour. This is the real mission. He installed it and took a picture of it. And despite my efforts, this is the only picture anybody has. Right there. That's the picture he took. It's the only picture anybody has of this thing in space. The Navy integrated this thing. They won't release any pictures. We got this one picture. So this is our kind of holy grail picture. From this picture, we can determine that everything worked out okay. So we have, or at least it survived launch. We have the 3 prototypes. Their antennas, in this case, they are in fact the single center-fed dipole antennas. And all this other stuff is, I don't know, some other cool experiment I don't know anything about. But these 3 are ours. The student whose work this really is, his name's Zach Manchester. He's right there, happily holding his prototype. I like this picture because it gives you a good sense of scale. You know, here's the satellite in this guy's fingertips, which is a very small part of this actually quite larger than a suitcase experiment. And then that massive, those huge solar panels on ISS. I mean, they really are immense. It's a big, big space structure, visible from the ground. That's a hard question to answer because it depends on how NASA will take things back down from space in the future. Historically, these so-called MISSI payloads, it's a material science experiment, historically they were taken back after about 18 months. So in fact, when they put this MISSI 8 pallet on here, MISSI 7 was taken back on Endeavour and then taken back down to the ground. And then they take a look at what kind of damage the radiation environment did to those components. So, but ours, it kind of depends on, are we getting a ride from the Russians? Are we getting a ride from SpaceX, from the Dragon capsule? It's not so clear. It's kind of good from that perspective, yes. Well, for us, if it hadn't been for the vandalism thing, our experiment would be done by now. We would already have gotten data, but now we know why we weren't getting data, or at least one reason why. But these also might have cooked in the sun. We'll see. We had.
Do you think somebody literally pulled it off?
Yeah, see, our ground station is about 2 miles away from campus. It's in the middle of a big field. Every now and then when we go up, it's also near an astronomy observatory. So every now and then when we go up, there's a new hole in the dome of the observatory where someone shot it with a .22. Once we went up there and found a whole bunch of half-eaten onions in a pile next to some beer. Like someone had stolen some onions from a field and then tried to eat them as part of a party or satanic ritual. I don't know exactly what they were doing. Yeah, so I can just imagine some clown, you know, hanging on the coax and swinging back and forth. You know, it's probably what happened, something like that. Because
the damage is on the ground, not.
It's on the ground, yeah. So as far as we know, this is okay. If you can swing from a cable in space, that'd be a fun hobby. All right, so I talked about why, you know, there's sort of an economic motivation to do this, but to me it's actually more about the physics. There are things we can do with these little tiny spacecraft that you can't do otherwise, and it's a point that I'm hoping to connect to rocketry here. So you've probably heard of solar sails, right? Not solar cells, which are what you use to get power from the sun, but solar sails, like a ship. The idea here is that with a large enough surface area and low enough mass, that is a large enough ratio of area to mass, a spacecraft will react to the photons from the sun. The photons carry momentum with them, and when they bounce off, they impart that momentum to the spacecraft. So this solar sail here would accelerate in response to photons. You know, we say the sun is beating down upon us, especially on a day like today, right? You really feel it beating down. Well, there is a very small pressure. So it's 1,362 divided by square root of light squared, speed of light squared, if you can figure that out. That's the pressure in pascals. Anyway, so it's very, very, very light force. It's negligible for us. But for a spacecraft, actually, so I know of a number of communication satellites that actually steer thanks to this effect. They actually orient their solar panels or other bodies on board to absorb torque and change their attitude in response to this. The space station actually flies in an attitude that balances solar pressure, gravity gradient torque, magnetic torque, and drag torque all at the same time. It's called a torque equilibrium attitude. And that's one of the terms in there. So it does matter when there's nothing else going on. You know, if you're out in space and it's just blackness, a little bit of sun goes a long way. So solar pressure is actually noticeable. Now, a thing that happens when you shrink down any body is that its ratio of area to mass gets bigger. And that's because area goes with something like length squared, mass goes with length cubed. So that ratio goes with, you know, squared over cube or 1 over the length. So if I shrink the length, that denominator becomes small, so the whole number blows up. So that area to mass ratio becomes huge for very small objects. That's why there are meteoroids called beta meteoroids that circle the sun. They're constantly being blown out of the solar system on just solar pressure. So these things escape the solar system just because of their size and without even trying hard. If we try as engineers to actually exploit this effect, I think we could do a lot more. So solar sailing is about that, but what we're proposing are solar sails that are much, much smaller, just because they're actually much more efficient. So yeah, it's not the Hubble Space Telescope on a solar sail, but it's something, and it's something that could go actually quite fast. The last thing I'll show you guys, in terms of hardware at least, is this. Now this one I'm going to have to hold up because it's really delicate, but this is a battery. It's a lithium-ion battery, and I'm going to hold it sort of on edge here. It's about 700 microns thick. It's really thin, but this lithium-ion battery, we can use this to power a beep from our chip all the way from Jupiter that we could see on the ground with a large enough antenna. So that's pretty cool. So this would be enough, turns out, using these special cell phone techniques to allow these little chips to talk to the ground from Jupiter. Now, I don't think we'd talk back to them because they're not very good at receiving information. We would need to use some massive dish on the ground to get this data. But that's kind of okay. If we have thousands or maybe even more, millions of these little chips doing something of scientific interest very far away, you might actually be able to get sufficient information to do some science with them, and without actually investing in a Cassini or a Voyager or one of these large, exquisite missions. So, solar radiation pressure might get you there. This is a prototype solar sail. You can see people down here. This is probably, I don't know if any of you know this, this is at Marshall Space Flight Center. I think this is probably the 30-meter cross-section one. This would be enough to provide decent propulsion for a spacecraft the size of the chair. So you see the problem. If you actually want to propel something the size of the space shuttle and actually send people somewhere using a solar sail, you need something kilometers across, the size of Maryland probably. That's what you would need. So this does not scale up very well. Not only do you need a whole lot of area, you also need this to be kind of stiff, right? You need to hold its shape. So you have all these ribs and truss elements and so forth, and even then it's very floppy. Well, that little battery I just held up at 700 microns, that's actually very close to the performance of this entire solar sail with its spacecraft. If we printed a circuit on that, we could get similar performance in terms of acceleration to this guy without actually going to the effort of building a 30-meter piece of material.
Does it have to orient itself a certain way to catch the photons?
Yeah.
I'm assuming?
Yeah, so that's the trick. I mean, I don't know if you're from Maryland, you've probably been sailing before, or know someone who's been sailing, right? You know how it's hard when that boom kind of comes around and swings around. It takes a long time. It's very floppy. Imagine how hard that would be with something that's only a few microns thick. It's very difficult. But that prototype is stiff, right? It's got high frequency. So it's actually quite easy to horse it around as opposed to moving this thing around.
What's the sail made of?
This, I think this is called CP1. It's a polyimide. They were trying to make an aluminized coating for Kapton, and they discovered they could take the coating off and use the coating itself. So that was, and this is only a couple microns thick. So it's actually very thin compared to what I'm talking about here.
Strong?
It's strong enough, apparently. So, I mean, they're able to deploy this in 1G, in 1 gravity. So it holds together there. But as you'd expect, I mean, it's only a couple microns thick, right? So it can't have huge shear stiffness. There are probably even better materials that use nanotubes or nanocomposites. They haven't tried those yet. But it seems that there's kind of a lower limit. You pretty much can't get too much better than a couple microns thick for these solar sails. And that's why I say that the additional degree of freedom to exploit is actually scale. Rather than making them thinner and bigger, just shrink the whole thing down. And then the math helps you.
Does it have to be a certain material to absorb the photons, or would anything work?
Anything will work, but it works better if it's reflective. So if it's, let's say, matte black and it just absorbs the photons, you'll get sort of 1 photon's worth of pressure. But if it can also reflect the photons, you get sort of 2 photons worth of pressure, if you see what I mean. There's sort of an incident photon and a reflected one, and you get kind of twice the result. So that's why these are always shiny. They try to reflect the photons. They try to be specular. Yes?
How would you aim it? I mean, on the sailboat, you have the keel and the center
Right.
board or dagger board to kind of counteract in the water. In space, you have nothing.
Exactly. That's
Running with the wind. Right?
That's pretty much it. Well, so what you do, of course, you would tack a little bit, right? So you hold it a little sideways, and say you're the sun. The photons hit here and impart momentum in that direction. But when they bounce off this way, it imparts a little momentum in that direction. So you can make it go diagonally, like hitting a pool ball on the side, right? It glances off a little bit.
It'd be a slide.
Right, but you'll never be able to tack into the, you'll never be able to sail into the wind. That can't be done, not with this anyway.
Would the photons want to spin it? It seems that once it's there, because there's nothing holding it, that it would have some reaction and start turning.
Yeah, you're absolutely right. So there are a couple ways to get around that. Most of the designs I've seen just use some kind of thruster to react that, which seems very inefficient, right? Because now you got a propulsion system on the solar sail.
See anchor.
Well, spinning it works, okay? So when you spin these solar sails, say spin it around this direction, that provides a kind of gyroscopic stiffness that prevents the photons from tilting them all the way around. It kind of tilts it the wrong way. It's like a helicopter rotor, right? It wants to stay in that plane, so when you try to process it, it wants to stay there. So spinning helps.
Aside from like spinning for passive stabilization, you got any ideas for, you know, actively steering these things or at least orientation controls? Maybe piezo gyro or something to that effect?
Well, so there's, I think, different answers for the big solar sails and the little solar sails.
For smaller.
Well, one of my favorite ideas, actually, a grad student came up with this at Cornell. Have you heard of a corner cube in optics?
Yeah.
Okay, so you put sort of 3 flat surfaces like this, and the inside of a cube, that shape tends to reflect exactly whatever comes into it. So you can actually make a corner cube out of 3 of these, making 8 little corner cubes within it, right? And no matter what direction it's oriented, it'll always exactly reflect the incident solar pressure. So you may not be able to control it, but you can at least guarantee what'll happen.
Right.
And if you design the trajectory right, maybe it'll get you what you want. So, and that's actually
You've got 1,000 of these up there, you're going to be getting something.
exactly.
Like a shotgun blast.
That's exactly the point. No, that's exactly right. And the thought here is that rather than spending the effort on, let's say, microscale gyros, which would be cool, rather than doing that, let's just launch 1,000 of them and hope that one of them gets there, right? Or maybe the 10 of them get there, but they're only 1 in 10 reliable.
How do
Okay.
you get them going and aim them to where you want to be in 6 years or something?
I think we would depend on statistics to help us out. So it's a project that we're doing right now, is to figure out just how many you'd have to launch at a given initial condition to have a suitable number at the end of the trajectory. And it could be millions here to get 10 there.
But would you shoot them out of a can with a spring or
Oh, I see.
something? Or, you know, how do you initially get it going and heading off to, say, Jupiter or something?
I think just putting them in the right place is the key thing. And then you'd sort of plan the trajectory from that initial condition. So using that corner cube idea, if we put it in a place such that constant radial force moves it in the direction we care about, then we're done.
So it's kind of starting almost from a stop.
That's the idea. So, but there'd be many ways to make this happen. We have other ideas for propelling these things. One of them is using outgassing, which you've heard of, right? So outgassing is this tendency of materials to lose matter in a vacuum. That is sublimation or boils away or something, right? That outgassing phenomenon means particles are leaving the chip, and we've shown this in the lab. We put a little chip on a vacuum and levitate it on a magnetic plate. You can see it torquing in response to that. So we could spin them up with outgassing. We can also force them in a certain direction with outgassing. Now we could also use propulsion. People have made propellant on a chip before, except it tends to blow up the chip. So I'm not a big fan of that one, but
That would be mine.
But having said that, I mean, honestly, I think I would be open to your suggestions. If you can think of any kind of propulsion behavior that is passive and easily initiated, safe, doesn't fall apart in a vacuum, and so forth, we want to hear about that. Okay, I'm going to end with this bit of science fiction here. So maybe some of you have seen this show by Michio Kaku on the Discovery Channel, or Science Channel, sorry. So it's called Sci-Fi Science, right? We did a show with him in which we talked about this particular idea. Put one of these chips in orbit around Jupiter. This is, by the way, a picture of Jupiter view from above, which we don't normally see, right? Normally see the big red spot, but here it is from above. Let's say that this chip is flying around Jupiter in orbit. Let's also say that it has an electrical charge on it, like an electron or a proton or any kind of subatomic particle with electric charge. You also understand that Jupiter has this hugely dense magnetic field. It's about 20,000 times as powerful as Earth's magnetic field. So we have a charged particle in a magnetic field in a circular path. This is called a cyclotron, or a particle accelerator. An interesting way to get a spacecraft of this size to a very high speed would be to put it in orbit around Jupiter, charge it up using some techniques I can tell you about, and then continually add energy, maybe from solar pressure or something else. And over the course of dozens or maybe even hundreds of years, this thing would acquire a very high speed. And whenever you turn off the charge, which could be done with electronics or some other way, it would rocket out of orbit on a very high speed trajectory. So I'm confident you could get maybe 1% of the speed of light using this trick, because that's, the math says that's easy. It would be harder to get 10% of the speed of light, but it's not completely out of the question. So that's a bound for you. I mean, I'll sign up right now to doing this if you give me enough money. But if you give me even more, I'll try for the 10% of the speed of light. That's an important number because, you know, getting to the nearest star from here at the speed of light takes something like 4.3 years. But no one's going to travel that fast. And even if you did, if you could travel that fast, you have to accelerate up to that speed first, which would take you some time. Unless you happen to be a photon, in which case you have other issues. Okay, but instead, the idea would be to get this thing going fast enough that it would travel there in a sufficient amount of time. So at a tenth of the speed of light, it would take 43 years or so to reach that nearest star. The trick with trying to leave the solar speed is that all of the resources you want to get to high speed are all in the solar system, right? If you try, let's say, using solar pressure, as soon as you leave the solar system, there's no more solar pressure for you. Or if you use chemical propulsion, that chemical propulsion you use up in a few hours at best, or ion propulsion in a few months, all of which you'd use in the first few months of life in the solar system. You'd probably use solar power to power that ion propulsion. So this is the only way I can come up with of keeping a body in the solar system to use the resources we have here, namely this delta V, this added velocity through solar pressure or whatever, and yet also accelerate it to high speed. So we're sort of trapping the spacecraft, making our own particle collider out of the planet Jupiter, and sending it off. So this is not going to happen tomorrow, by the way. This will take some effort, but it's at least a path forward for those of us who are nutty enough to think that we want to go to distant stars someday. Now, I don't pretend to be able to ride on this thing, although, you know, one thing we could do would be to encode someone's DNA. So if we, let's say, call Richard Branson, who has maybe a lot of money, and say, well, we'll sequence your genome and print it on the chip and send it off to the nearest star. Maybe he'd go for that. We'll see.
I guess dilithium crystals are out.
I don't have any of those, so if you do, I'm glad to hear about them. Okay, so I also have a clip of that movie from Michio Kaku, but I think I spilled all those beans already. So if you want to see the movie, I can show it to you. Otherwise, all right.
We scientists don't spend all our time buried under a book, stuck in a laboratory. Sometimes we like to do something completely wild to give us a fresh new perspective. And I like to escape. I designed an army of self-replicating swarm bots. They'll seek out habitable planets and manufacture all the infrastructure our future colonists will need. But there's a huge problem to overcome. The distances my swarm bots will have to cover are immense. Let's say one circuit around this ice rink is equivalent to the distance from the Earth to the Sun. That's 93 million miles. In comparison, to reach the nearest star, Proxima Centauri, I'd have to travel around this rink 250,000 times. And if I wanted to reach the outer edges of our galaxy, I'd have to do more than 6 billion circuits. Even for Han Solo, it's a big task. I need to figure out how I'm going to cover these huge distances. This guy's going to show me. Meet Mason Peck, spacecraft engineer and sci-fi fan.
We've got plain water here. I'm going to add some baking soda to it. That dissolves in the water and separates into charged particles. They're attracted to these two electrodes here, positive and negative. And there's a current now flowing through this water. If I add a magnet, the magnet causes the particles to move in a circular path. Now, it's a little difficult to see, so let me add some pepper. Maybe that'll help illustrate just where these particles are moving. If you look closely, you'll start to see this swirling motion.
That's the Lorentz force, right?
Exactly right.
Charged particles move in a circle in a magnetic field.
That's exactly right. So the magnet is what makes this possible.
Now, here's the killer question. How can you use this as a propulsion system to shoot things into space?
Right. You'd need a huge magnet. And fortunately, we have one in the solar system, and that's Jupiter's magnetic field. What we'd have in mind would be to make a spacecraft small enough that can act as a charged particle in the magnetic field of Jupiter.
Any small spacecraft with an electric charge will stick like glue to Jupiter's magnetic field, which means that I could accelerate them to high speed as they orbited the planet.
At some point, you turn off the charge. When you turn off the charge, they go zinging away.
How fast can you propel a chip or a particle this way?
What we think we know how to do now is maybe a few thousand miles per second, and that's a noticeable fraction of the speed of light. A few hundred years from now, I don't see a limit. I mean, there's no reason why this couldn't approach the speed of light.
Approach the speed of light. I mean, that's huge, right?
It's a lot of speed.
Jupiter's huge magnetic field is 20,000 times more powerful than that of the Earth. Mason's idea to use it as a springboard for my swarm bots may be centuries into the future, but it's a stroke of genius. If I give my swarm bots an electric charge, I can bind them to the magnetic field of Jupiter. Once I've accelerated them to near light speed, I can switch off the charge to slingshot them in all directions across the galaxy, where they'll build colonies on habitable planets.
Okay. Yeah, you're not going to hear this. Sorry. So there's 3 of me in our lab. I'll narrate this since you can't hear it. So this is a demonstration of the physics of that behavior. This is water. We put baking soda in the water, which then dissolves into positive and negative ions. We put a big magnet underneath it. And as those particles are attracted to the positive and negative end of this battery that we've got here, you can see how they start to form a circular pattern. That circular behavior, that's due to what's called the Lorentz force. That force is the same force that keeps our CHIP satellite bound to the planet Jupiter. All right, so that demonstration I thought was pretty neat. I had a graduate student put that together in about 4 hours, starting about 3 a.m. the day before he came. So you can see that swirling pattern. So this is just without trying very hard. And here he's showing, take these little CHIP satellites, put them in orbit around Jupiter, in Jupiter's magnetic field. You can see the dipole lines. And as they go faster and faster, then off this thing goes. But okay, so that's the science fiction end of this talk. In the near term, like I said, we'll build this next generation prototype which shrinks down the nickel sat. You see the nickel on the back. It shrinks this thing down into a easily digested size. You can pass it around if you want. And now I have the trivia question for you. Why is there a nickel on the back of this prototype here? Any guesses? So it's not a good reason. What's that?
You lost a bet?
It's close. Close. So, all right, so you see that this is covered in kind of a goopy substance, right? It's called aerethane. It's a conformal coat. What you do is you coat electronics with this stuff to keep them rigid and maybe protect them from other things. Okay, so I had a student do this. It was his first time doing it. He thought a good idea would be to prevent the prototype from sticking to the lab table by putting a nickel underneath it to keep it up above the table. But of course, then the aerethane ran down and glued the nickel onto it. So it's an accident, and in fact, this one was supposed to go onto the space station. We would have had 4 up there, but we couldn't convince NASA that the nickel was flight rated, so that's the way it goes. Yeah, poor Tom Jefferson almost made it into space, but he didn't quite. Okay, anyway, that's it for the slides, but I'm glad to keep talking about science fiction if you want. Thank you.